Okay, so good evening, everyone. This is TA lecture for the course of Introduction to Commutative Algebra and Algebraic Geometry. And in the last lecture by Professor Dilip Patil, it consists of lectures on Noetherian module, Artinian module, and some properties for both of them. Now, uh, uh, there is no point in repeating the definitions of these two modules and also rings, that is Noetherian rings and Artinian rings. And a Noetherian ring is nothing but a ring which is a Noetherian module over itself, and an Artinian ring is a ring which is a module over Artinian module over itself. So yeah, so my objective is to do some tutorial assignments, and I will start with that without wasting much words. So tutorial assignments. Since there is not much student, so I will assuming that you have no doubts. So I will be writing problems and doing solutions. So first question, prove that a finitely generated Z module M is Artinian if and only if M is finite. By finite I mean finite Z module, that is it is generated by finitely many elements. So now prove if M is finite Z module, that means if it's generated by finitely many elements, then one can like any descending chain you take, and you will see that since it is finite, so all the descending chains should be finite, so then it is Artinian. This finite means cardinality is finite. Cardinality. That makes sense. So if there are only finitely many elements, for example, take M as uh, z by some nz. Now we assume for the converse M is finitely generated Artinian Z module. Then by the uh, like classification theorem, that is any finitely generated module over a PID can be written as direct sum of torsion and free module. So the structure theorem for modules by structure theorem. Where z by dkz. This is your free part, this is your torsion part, and d1 divides d2 to this. Now since M is Artinian and we know that Z is not Artinian module over Z, so f is 0. I mean ZF should be 0. Why this is not Artinian module? Because can take 2z, z obviously, 4z, 8z, like this, and this descending chain never settles, infinite. So this infinite chain never settles. So the question was that prove that a finitely generated Z module M is Artinian if and only if M is finite, that is cardinality is finite. So if M is finite, then it is Artinian because it has finite cardinality, so any chain you take it will settle. And for the converse part, we are assuming that M is finitely generated Artinian module. Then by structure theorem, you will see that M is direct sum of free module and torsion module. And since M is Artinian, you will see that Z is not Artinian module, because you see that Z can be written down in this Z2, Z4, Z8 is. So this free part should be 0. Now hence M should be of torsion from, that is d1z direct up to z by dkz, that is m is finite. So our first assignment is done. Now for the second question, let A be a commutative ring and M be a Noetherian A module. Prove that A by AN, that is annihilator of a module, is a Noetherian ring. Okay, I'll define what is annihilator of M. That is of A such that A dot M for all M belongs to A non-zero. Okay, so take 5 minutes, then we can discuss about this, to think about it. Okay, so we'll be discussing the solution proof. Since M is a Noetherian A module, M is finitely generated A over A, because you know these are two equivalent notions, that is Noetherian and this finitely generated over A, not equivalent, because in a finitely generated module may have infinitely generated submodule, but if M is Noetherian, then M is finitely generated. How do you get this? So that this should be a submodule over itself, so that is how it would be finitely generated. Now let M1 to Mn be a generating set of M consider the ring homomorphism phi A to 1 to n of M. Defined by 1 going to M1 to Mn, can easy to check that. Now claim is that car phi equals to annihilator of M. So let's prove that first. Let A belongs to car phi. That means A dot Mi equals to 0 for all I. Now M is generated by all these mi's, so A belongs to annihilator M, right? Because any element M can be written as the scalar sum of scalar multiples of Mi, so that would mean that A dot that M should be 0, and so now for converse let A prime belongs to annihilator of M. Then this is easy, right? Then A dot Mi should be 0 for all I, because Mi belongs to M. So A prime should be car phi. That is so it is done. Now Therefore, A by car phi equals to A by annihilator of M, which is isomorphic to phi of A. That means the image. Since finite direct sum of Noetherian modules are Noetherian, I equals to 1 to n, M is a Noetherian A module, some module is also Noetherian. That is, at least we know that this annihilator of M is Noetherian A module. But our goal is to show that ANN by M is Noetherian ANN by M module, right? But this is equivalent to showing this ideals I bar of M is finitely generated over, but we can get back to that, but not that we don't need to write this because these are equivalent and you already know. So if I bar is an ideal of A by A n and M, then I bar is an A submodule of A by A n and M, right? Therefore, I bar is finitely generated as an A module hence is finitely generated as an ideal. Just take the images in mod and those elements should generate that ideal. So this is clear, right? Quite trivial that. Therefore, so A by A n n M is a Noetherian ring Okay, so yeah, now we will be doing a very good uh, uh, exercise. I will give you 5 to 10 minutes for this because this is a two-part question. For a let M be a Noetherian A module and U to M a module homomorphism. The interesting fact is that if U is surjective, then U is an isomorphism. And you can guess that an analogous result if M is Artinian and U is injective, then again U is an isomorphism. So this is quite intriguing, right? Because it's kind of reminiscence about this vector space theorem, right? For linear operators, that if it is injective then isomorphism, also surjective then isomorphism for finite dimensional vector space and for any linear operator between them. So here also, if you take M as Noetherian A module and if you have surjective homomorphism, at least endomorphism between them, then so if you have an epimorphism between them, that is an isomorphism, and if you have a monomorphism between them, so that will be an isomorphism for Artinian case. So yeah, take 5 minutes to think about this, and then we'll get back to this. Excuse me. So class. So yeah, you should do it. For proof. So for the first, yeah, it is easy to check that we have an ascending chain of submodules, obviously. Car u square where by car un where ui are the compositions map, because you know that this endomorphism of M as endomorphism of M is an A algebra under class and composition map. This has multiplication. This acts as multiplication. So yeah, now since AM is Noetherian, there exists K belongs to N such that car of UK equals to car of UK plus 1. Now notice that UN to M to N is surjective for all n belongs to n. Since U is surjective, right? Because this is clear. You just take one element from the end of this composition and go proceeding one by one, and you go to your domain. So in particular, UK is surjective, right? Particular UK is surjective. Now for any x belongs to car U, there exists y belongs to M such that UK of y equals to x, right? Then UK plus 1 of y is UK of x, right? Sorry, y. So U of x should be 0, which implies that y belongs to car of UK plus 1 is equals to car of UK. Therefore x equals to UK of y to 0. Hence car of U equals to 0. Now since x is arbitrary, in car U, right? So that is U is injective, and we had that U is surjective implies U is an isomorphism. So what we did really is that we chose an element from car U, that is x. It showed that belongs to UK is surjective, so there exists y such that UK of y equals to x, and again UK of y should be 0, that is x. So yeah, x is arbitrary in Caryu, so all the elements in Caryu should be 0. Now the part B proof should be similar, but anyway I have to do it. So it is easy to check that we have a descending chain. Im of u square Im of u to the power n of submodules of m. Since m is Artinian, there exists k of n such that image of UK should be equals to image of UK plus 1. Now in a similar fashion, UN is injective for all n belongs to n, as obviously u is injective. In particular, UK is injective. For any x belongs to n, there exists y of n such that UK plus 1 of y should be UK of x, since UK of x belongs to image of UK equals to image of UK plus 1. But then UK u of y minus x should be u of UKY minus UK of x, which is equals to UK plus 1 of y minus UK of x. But these two are equal, as we have earlier assumed, which implies that u of y minus x should be 0, that is u of y equals to x, since obviously uk is injective, hence image of u should be m, since x is arbitrary in m, that is u is surjective, so u is an isomorphism. Okay, so this is quite a good result. Now again we have seen what is a spectrum of a ring, so we'll be doing a application to this spectrum. Okay, let's see. Actually this is quite important in number theory and both in algebraic geometry, as you'll see that this will be definition for Dedekind domain and or Dedekind domain, whatever you say. So but yeah, it should be question number 4. Let A be a Noetherian ring prove that the following are equivalent. So first one is Artinian, spectrum, that is the collection of all prime ideals with Zariski topology, discrete and finite, and the third one is that spec A is discrete. So again take 5 minutes to think. So yeah, let's do this let's do the solution. So we'll be going from first A to B. If A is Artinian, then we'll not be doing the proof of this result, that then every prime ideal is maximal. Look at Atia McDonald, chapter 8. Okay, that is P is closed in spec A, because know that V of P is equal to P closure, which is only P itself, because this is maximal, right? So it's closed. Also there are finitely many maximal ideals of A. So again, using a well-known result, I hope this will be done in the next class, next week, that an Artinian ring has finitely many maximal ideals. So spec A is finite, right? And any topology on a finite set is discrete. So spec A is discrete. So from B to C is obvious. Now for 3 to 1, that is, this is little non-trivial, that if spec A is discrete, then we have to show that A is Artinian. But since spec A is discrete, every point set P is closed. Hence, every prime ideal is maximal and A is Noetherian, remember? And from this result that every prime ideal is maximal, I should have told you that what is Krull dimension. This is the increasing chain of prime ideals, maximal length of increasing chain of prime ideals, and there is a result that one dimensional Noetherian ring is Artinian. So I'm sorry that I should have checked this solution. Okay, so A is Artinian, but anyway, these kind of things one can learn from their own and follow this beautiful result. Actually, it's quite difficult to follow the syllabus thoroughly and make solutions, because in classes not everything you are told, but when you actually look into doing problems, so many concepts are required. So I would request you to follow these terms, that Krull dimension and those kind of things. Okay. Since you are not yet introduced to localization, I would not tell you if Noetherianness is local property or not. Actually, it is not. The converse is true, that if A is Noetherian ring, then every local ring is Noetherian. Okay, let's see how many problems do I have, because all the problems require some at least some advanced knowledges. Okay, I'll check, give me 1 or 2 minutes. Okay, okay. Uh, let's do this problem. I think this can be done. Assume that R has a unique maximal ideal P and let A be an Artinian R module for small p belongs to P and x belongs to A. Prove there exists n then 1 such that Pn of x should be 0 conclude that if P is finitely generated then for each x belongs to A there exists R greater than equals to 1 depending on x such that PRX equals to 0. Okay, read this question carefully and we'll see its solution. It is actually an interesting problem. Let's see. So we'll be doing this proof. Okay, now for x belongs to A, that is an R module, Artinian R module, and small p belongs to P, we can form a descending we can form a descending sequence of some modules that is from Px containing P square x, like this, right? And hence there exists n greater than 1 such that Pn of x should be equals to Pn plus 1 of x, right? So it follows that Pn of x are Pn plus 1 of x for some R of R. Thus one minus Rp of Pn dot x should be 0. That means you are just subtracting R of P to the power n plus 1 of x and just taking common. However, since P is the only maximal ideal of R and 1 minus Rp doesn't belongs to P, because since small p belongs to P, so small r small p belongs to large P, and if this element belongs to P, then 1 should belong to P, but P is maximal, so it is proper. Okay, so we have 1 minus Rp is a unit, because again, if 1 minus Rp is not a unit, then it should belong to a proper ideal. Just take its take the ideal formed by this, and every proper ideal should be contained in a maximal ideal, and the maximal ideal is unique, so 1 minus Rp again it would belong to the large P, but since it is not non-unit, so it has to be unit. Thus so cancelling the unit, we get P dot nx should be 0, hence proving our first part of the proposition. For some n, now coming to the second part. Suppose P equals to P1 dot 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 PC is finitely generated. Fix x belongs to A. Then for each I we have Pi Ni equals to 0 for some Ni Nc greater than equals to 1. Now if we set n equals to max of if we set n equals to max of n1 up to nc, we have P1n to Pcn of x is to 0. So by the pigeonhole principle, for r greater than equals to 0, I mean much bigger P of R should be contained in P1 of n to Pc of n, which will give us giving P of x should be 0. So we are done, right? If you have any doubt regarding this, you can ask me in the mail, which I have repeatedly giving. Now I will be proving one result that if R is Artinian ring, then R has finitely many prime ideals. So I will be proving this result, that is let R be an Artinian ring A, prove that R has finitely many maximal ideals. Actually, this result I have used before, so be careful about that. And for the second thing, anyway, I will do this. Let J denote the next Jacobson radical that is the intersection of all maximal ideals prove that this is actually nil radical, that is J equals to 0 for some n greater than equals to 1. So since I have been talking rigorously, so take 5 minutes to think, and we'll be doing this from 7:36 or 7. Okay. So this will be our last problem for today, because the second one might take me to 10 minutes to prove. Yeah. Okay, so the terms you're asking, so I guess you are asking what is Artinian ring. So I have already told that Artinian ring also was discussed in the class, that yeah, I'm not writing it, but listen carefully. That is, Artinian ring is a ring that is Artinian module over itself. So if A is your ring, Artinian ring, then you can think of A as an A module, right? So that A, when you think of it as a module over itself, it should be Artinian module. That means what? That every descending chain of submodules, that is, if you are going down, should be finite, and you know that in a ring every submodule is no, yeah, I mean, yeah, I mean A cross, so the scalar map should be like this. If you given A as ring, so when you think of A as an A module, so the scalar multiplication should be like this. R A should go to RA, and obviously it is an abelian group, and the properties are distributive, behaves well, so it is an A module. So when I say that A is an Artinian ring, this A should be Artinian module over itself, over A. So this package is Artinian ring. So now clear? I mean, at least this definition. Yeah, okay. So yeah, now we know what is maximal ideal, that is uh, uh, that is a proper ideal which is a maximal element in the set of all ideals, all proper ideals. And Jacobson radical, that I have just explained, that it is the intersection of all maximal ideals. And yeah, so if you, when you are taking to the power n, means you are taking all the powers. So if it is okay, I am erasing this. Okay, so okay, uh, let's start the proof and okay. So we will do this by contradiction. Suppose there are infinitely many distinct maximal ideals of R, say P1, comma P2 dot dot dot, then we have a descending chain of ideals it is P1 intersection P2, P1 intersection P2 intersection P3, and so on. So thus for some n greater than equals to 1, P1 intersection P2 Pn should be equals to P1 intersection P2 intersection Pn intersection Pn plus 1. So it follows that P1 intersection up to Pn is contained in Pn plus 1, right? Now, since Pn plus 1 is a prime ideal, we have Pi contained in Pn plus 1 for some I, right? This is from Atiyah's first chapter, that is, if a prime ideal contains intersection of some prime ideals, then it should contain one of them. I will mark here chapter 1, maybe 1.11, 1.12, I don't recall clearly, but you can see it there. So yeah, since Pn plus 1 is a maximal ideal, we have the contradiction Pi equals to Pn plus 1, right? Because we started with infinitely many distinct maximal ideals and we are seeing that one of them is equal to other. So from this, if you eliminate this and again start the operation, you will see that it will keep happening, and until you see that there are only finitely many R has finitely many maximal ideals. Okay, so I started with infinitely many distinct maximal ideals. So P1 up to P2 and P2 up to infinite. So uh, my claim is that it has only finitely many maximal ideals, and so if they are distinct, then you should know that uh, P1 should not contain P2, because as they are maximal, so if one of them contain other, they should be equal, right? So none of them should contain any of them. So if I then use the Artinian property of the ring, then you can see that at least one of them is contained in another. But I started with distinct maximal ideals. So it contradicts that, na? That the fact that the distinct properties of maximal ideal, it contradicts to that fact that P1 is contained in Pn plus 1. So Pn plus 1 equals to P1, Pi, which is not true. Okay, then I will write it where. Uh, huh, Here we have the contradiction. Yeah, okay. The yeah contradiction to the fact of distinctness. Okay, so let's go to the second one, which is, let J denote the Jacobson radical and intersection of all maximal ideals, which is the Jacobson radical, and prove that J should be J to the power n should be 0 for some n greater than equals to 1. Now since R is Artinian, there exists n0 greater than equals to 1 such that Jn equals to Jn plus 1. J is your Jacobson radical for all n greater than equals to n0. Now since J is contained in J square, J cube, like this, right? On the other hand, suppose my Jn is not 0, then there exists x1 belongs to Jn such that x1 of Jn not equals to 0. Just pick x1 as non-zero element and you'll see, since if x1 of Jn would be 0 for all x1 of Jn, then Jn dot Jn, that is j of 2n, and this is Jn because you already see that this one would be 0. So at least there should be one x1 such that x1 of Jn not equals to 0. This is contradiction. Now choose x2 Jn such that x1 dot x2 dot Jn not equals to 0. We can do this, right? We can do this. Otherwise, if say x1 x2 Jn equals to 0 for all x2 of Jn, and thus 0 equals to x1 of Jn to Jn such that x1 of j2n and x1 of again Jn, which is contradiction to the choice of x1, where so let me put this in brackets so that it does not interfere with the main proof. So thus inductively we can find x1 x2 Jn such that for all c greater than equals to 1 x1 dot 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 xc of Jn not equals to 0. Now the descending chain x1 x2 this must stabilize. Because it is an Artinian ring, so the descending chain of ideal should stabilize. Thus, for some e greater than equals to 1, we can write x1 dot dot xc to r of x1 dot dot xe plus 1, right? That means what I'm saying, that is using x1 to xc equals to x1 to xe plus 1. Yeah, for some r belongs to r. Thus, again similarly 1 minus r x of e to the power 1 x1 to the power xn up to xn xe should be 0, since x e plus 1 belongs to j, 1 minus r x e plus 1 is a unit. I have already told this in the previous part of the proof that if x e plus 1 belongs to j, then its power, its scalar multiple also belongs to j. So if this belongs to j, then 1 should belongs to j, which is contradict to the fact that this does not belongs to j. And if an element does not belongs to j where j is unique maximal ideal, then it should be unit, because if it is non-unit, then the ideal you form with this would be a proper ideal, and it would be contained in a maximal ideal. So it would be contained in j, since j being unique maximal, so it has to be a unit. Thus x1 xe 0, a contradiction, because since this is unit in this multiple, so you can cancel out the first part, so this multiple should be 0. So this is a contradiction, because if Jn was non-zero, then you would see that all these terms, that x1 x2 and this inductively the multiples you would be getting, those would be all non-zero. So contradiction, therefore Jn equals to 0. So we are done. So actually since you have missed some classes and also major part of this assignment, we started with some simple problem that any Artinian Z module M should be finite. Then this beautiful result that A by annihilator of some module always a Noetherian, where M is Noetherian. Okay. Yeah. We will be getting those slides. Already all these slides are previous slides are available in the, I think, NPTEL website on NOC. I don't know what NOC is. I think that the website you are telling about, you will see below the lectures there will be something called January 2025 TA classes. So there you will be seeing these slides, and yeah. Right. So there will be all the links for the lectures, and all the slides are available. Yeah. Okay. Thank you for joining. We will be meeting on the next. Thank you. We will be meeting on the next class, next Tuesday. Yeah. Okay. Bye.